Have you ever crushed a sugar cube in the dark or bitten into a wintergreen candy and noticed a faint spark of blue light? This seemingly magical glow is not a trick of the eye. It is a real physical effect known as fracture-induced luminescence, or more broadly, triboluminescence. The term comes from the Greek tribo, to rub, and lumen, light, and it refers to the phenomenon where materials emit light when subjected to mechanical stress such as rubbing, pulling, or fracturing. But why would breaking something produce light? To explore this, we need to look at the atomic and electronic structure of crystals. In many crystalline materials, particularly ionic or asymmetric ones, mechanical stress causes a sudden realignment or rupture of internal chemical bonds. These fractures rapidly separate regions of positive and negative charges, creating a brief but intense electric field across the crack. Much like a lightning bolt, this field can accelerate free electrons to high energies. As these electrons collide with atoms or recombine with holes, they release energy in the form of visible or ultraviolet photons, creating a flash of light. This process is not purely mechanical. It is deeply tied to the electronic and lattice structure of the material. The most famous everyday example is the hard candy-containing methyl salicylate wintergreen oil, which fluoresces bright blue when chewed in the dark. The glow is due to both the mechanical generation of ultraviolet photons and the subsequent fluorescence of the methyl salicylate, which absorbs UV and re-emits visible blue light. But even plain sugar crystals, without any additives, exhibit weak triboluminescence, suggesting the effect is more widespread than we typically notice. So why does this not happen with everything we break? The key lies in symmetry and charge distribution. Materials that lack a center of symmetric crystals are more likely to produce triboluminescence because the internal charge separation during fracture is asymmetric and can create a large enough electric field. Quartz, sucrose, and some rare earth dope materials are good examples. Symmetric crystals, on the other hand, tend to distribute stress more evenly, reducing charge separation and the resulting emission. Interestingly, certain materials are engineered for this effect. For example, europium-doped crystals, zinc sulfide, and other phosphors are designed to glow vividly when cracked, making them candidates for stress sensors in smart materials. Some research groups have proposed embedding these luminescent crystals in structures like bridges or aircraft components to visually signal the presence of microscopic failure occurs. Another related phenomenon is mechanoluminescence, where not just fracture, but any mechanical deformation, like bending or compression, can cause light emission. In some materials, repetitive cycles of mechanical stress can even produce a steady light output, suggesting potential applications in energy harvesting, for example, converting footsteps into light. This overlaps with research into piezoelectric and triboelectric nano-generators, where mechanical motion is used to generate electrical energy. Could this glow be used for something practical, or is it just a curiosity? Beyond structural health monitoring and novel sensors, triboluminescent materials are being explored in the field of security and authentication. Since the emission patterns are unique to specific compounds and conditions, they can be used as invisible tags that light up only under mechanical stress, useful for tamper detection, anti-counterfeiting technologies, or secure packaging. There is still much we do not understand. Why do some materials glow strongly while chemically similar ones do not? Why does the emitted light vary in color? And can we design materials to glow on demand with predictable wavelengths and intensity? Fracture-induced luminescence is a vivid reminder that even destruction can reveal hidden beauty, and that mechanical failure, far from being silent, might be nature's way of whispering its secrets through flashes of light. When a crystal is fractured, bonds snap and electrons are ripped from atoms, creating separated positive and negative charges on the newly exposed surfaces. These charges generate intense local electric fields, sometimes millions of volts per meter, that accelerate electrons across microscopic gaps. As these high-energy electrons collide with gas molecules trapped in cracks or with luminescent centers in the crystal lattice, they transfer energy and excite atoms or molecules. When these excited species relax back to their ground states, they emit photons in the visible range. The overall process, transforms mechanical work into light, with efficiency depending on how readily the material sustains charge separation. This explains why only certain crystals, those that permit large surface fields, exhibit strong triboluminescence. Breaking sugar crystals coated with a thin film of adhesive tape in air produces bluish sparks as accelerated electrons excite nitrogen molecules. It's like rubbing a balloon on your hair to build up static electricity, then watching a tiny spark jump when you bring it near a wall socket, only on a much smaller scale inside the crystal. Only non-centrosemic crystals, those lacking a center of inversion, can support the piezoelectric effect necessary for triboluminescence. In these materials, mechanical strain induces a dipole moment, amplifying charge separation at fracture sites. The greater the piezoelectric coefficient, the higher the surface potential achieved under identical stress. This intrinsic polarization directs electrons preferentially toward one fracture face, producing asymmetric recombination zones that light up. Conversely, centrosymmetric crystals quickly recombine charges without creating significant fields and thus remain dark. Hence, materials like quartz, tourmaline, and rochelle salt are classic triboluminescent substances. Cracking a quartz crystal under compression yields a faint blue flash, whereas glass centrosymmetric produces none. It's like a one-way valve that lets water build up pressure on one side before releasing it. Only the water is electrical charge. Lattice defects, impurities, and intentionally added dopant ions create localized energy levels that can trap and then release electrons or holes. These trap states modulate the color and intensity of the emitted light by altering the recombination pathways. For instance, adding manganese ions to a triboluminescent host shifts emission toward orange-red wavelengths instead of the usual blue-green. A higher concentration of defects increases the density of trap sites, boosting photon yield, but too many defects can quench emission by providing non-radiative decay channels. Optimizing defect and dopant levels is thus critical for tailoring triboluminescent performance in sensors. ZNS crystals doped with Q2+ exhibit bright green triboluminescence, whereas undoped ZNS remains almost dark when crushed. It's like seasoning a dish. Just the right amount of spice transforms a bland meal into a vibrant feast, but overdo it, and the flavor collapses. The surrounding atmosphere plays a pivotal role. Gas type, pressure, and humidity all influence electron collisions and de-excitation pathways. In air, at atmospheric pressure, nitrogen and oxygen molecules act as primary collision partners, emitting characteristic lines, e.g., the blue of nitrogen. At low pressures, fewer collisions occur, reducing light intensity but shifting spectra toward material-intrinsic emission centers. In inert gases like argon, electron energy is lost less to gas excitation, enhancing direct crystal center luminescence. High humidity can quench triboluminescence by conducting away surface charge more rapidly. Thus, controlling the fracture environment is essential for consistent observations and applications. Triboluminescence from sucrose crystals is 50% weaker at 90% relative humidity compared to dry air. It's like fireworks. Light shows depend not only on the powder, but also on wind and humidity affecting how sparks travel. Optiluminescent flashes are extremely fast, lasting microseconds to milliseconds, and often comprise multiple spectral components. Time-resolved spectroscopy reveals initial high-energy violet emissions followed by longer wavelength green or red decay tails from dopant centers. The prompt emission corresponds to gas excitation by electrons, while the slower phosphorescent component arises from crystal lattice trap release. Spectra and kinetics therefore encode detailed information about charge dynamics, trap depths, and local fields. By analyzing these, researchers can deduce material properties and fracture mechanisms at the microscale. Fast photomultiply recordings show a sub-microsecond UV pulse in fractured quartz, followed by a 10 minutes green phosphorescence from defect centers. It's like a sparkler. First the intense bright sparks, then lingering glows as embers slowly cool. Capturing triboluminescence requires high-speed detectors, photomultipliers, or fast CMOS cameras, synchronized with mechanical actuators to trigger fracture. Spectrometers with nanosecond gating resolve the spectral and temporal evolution of the light. Sophisticated setups also include vacuum chambers to control atmosphere and electrostatic probes to measure surface potentials concurrently. Piezoelectric sensors monitor the applied stress, allowing correlation of mechanical energy input with photon output. These combined measurements yield quantitative efficiency metrics, photons per joule, critical for sensor development. A custom setup using a drop weight impactor and gated spectrometer quantified 10,000 photons per micronewton of applied force on ZNO crystals. It's like filming a pop rock candy explosion in slow motion with high-speed cameras and spectrometers to understand every sparkle. Triboluminescent materials embedded in composites can serve as visual indicators of microcrack formation under load. As cracks propagate, emitted light signals the location and severity of damage in real time. This enables non-destructive testing of structures from aerospace components to civil infrastructure by simply monitoring light emission patterns. Wearable triboluminescent patches also promise monitoring of joint stress or impact injuries in sports medicine. Furthermore, mechanical luminescent coatings on pipelines could alert to stress concentrations before catastrophic failure. Such applications leverage the direct correlation between mechanical damage and photon output. Embedding blue-doped Casnos particles in a polymer matrix allowed crack detection under tensile stress via visible blue flashes. It's like coating a bridge with paint that lights up where cracks form. Spotting damage before it worsens. Engineering devices require selecting host crystals, dopants, and matrix materials that optimize photon yield, color, and mechanical compatibility. Composite films often mix triboluminescent powders with elastomers to combine flexibility and luminescent response. Micropatterning techniques create pixelated arrays for spatially resolved stress mapping. Electrical readout modules convert light pulses into digital signals, enabling automated monitoring. Scaling from single crystal tests to large area devices involves managing uniformity of particle distribution and fracture mechanics. Successful design balances sensitivity, durability, and integration with standard structural materials. A flexible patch of doped Betio-3 nanoparticles in PDMS generated clear, dry bioluminescent signals under human joint bending. It's like embedding tiny glow-in-the-dark beads in a silicone bandage that lights up when you overstretch your muscle. Despite decades of study, key questions remain about the microscopic charge dynamics and ultimate limits of mechanoluminescent efficiency. The interplay between quantum confinement in nanocrystals and triboluminescent intensity is largely unexplored. Developing room-temperature, high-efficiency mechanoluminescent semiconductors could revolutionize stress sensing in electronics. Integrating triboluminescence with optical fiber networks promises remote structural health monitoring in inaccessible environments. Advances in computational modeling of fracture-induced charge transport will deepen our fundamental understanding. These frontiers bridge materials science, photonics, and mechanics toward a new class of smart materials. Recent theoretical work predicts that 2D piezoelectric materials like MOS2 monolayers could exhibit ultrafast triboluminescent pulses when mechanically exfoliated. It's like discovering a hidden superpower in everyday materials. Break them and they light up, opening new possibilities for sensing and display.